We're starting section 4.1, linearization and differentials. Linearization, differentials, approximations, and a relative error are on our list. So what is a tangent line? Tangent line is the line that touches graph of y equal to f of x at a point a and f of a. Why f of a? Because I have to point on the graph, I have to plug in the x value to get the y value. And the slope of the tangent line at a is going to be f prime of a. So you take the derivative, you plug in a. And so we can think of tangent line equation itself as a function of x. Remember, what was the tangent line? Was y is equal to y at a, which is f of a, plus the slope, which is f prime of a, times x minus a. And so this is, now if a is the constant, right? You're saying tangent line at point a. And so this becomes a function of x because you see that x over there. And so we call this function L sub a of x. L for linearization, a for at point x. That's how it goes. So given a function y equal to f of x, for x values near a, the tangent line L sub a can be used to approximate the function f of x. And how does this work? Basically, if the distance of the point B from the point A is small, then plugging in B in the original function is giving you a value very close to plugging it into the tangent line. Look at this picture. Right close to point A, the blue curve is very close to the tangent line orange line. And so over here, see, this is the box. Around that box, it's safe to use the value, y value on the orange line to approximate the y value on the blue curve. Here, for A is here and B very close to A. If I draw the vertical line, I get to the y value on the blue curve. But that y value is very close to the y value on the orange curve. And so instead of calculating the y, and we know that when its function is curvy, it means, like, for example, this one is a polynomial, the blue curve. And I know it's a polynomial because I plugged what I graphed here was a polynomial. And so this is a polynomial, and I'm looking at plugging in anything in a polynomial of orders more than one is going to be computationally somewhat heavy. But plugging in values in a tangent, in a line, is going to be much easier to compute. So I plug in stuff in the tangent line, and I get an approximation to the blue line, basically. And that's the purpose of approximation with the tangent lines. Now, again, we're saying that it's going to be easier, so we're going to give you an example. Square root of 3.98. From grade school, what would you do to approximate this? From grade school, you know that you go to a nicer value that you can take the square root, and then you use that to approximate. So what's a nicer value? Square root of 4. Now, as I'm writing square root of 4, I realized that in grade school, I used a function to approximate that. And this is literally a function plugged in, and you plugged in 3.98. So what's that function? It's f of x equal to square root of x. In grade school, we use just the value of the function to approximate and a nicer point to approximate. In Calc 1, we're going to use the tangent line to approximate. So we basically add or subtract something from the value of the function. In Calculus 2, you use series to approximate the function. So you use some information with second derivative, third derivative, all the way to actually approximate the value of the function. And so that actually the series, what you learn in Calc 2 is how your calculator computes the values of functions at different points. They use fixed points to find the tangent line, and then the fixed point to approximate, and then they use the series around that fixed point to find all the other values. Here we just use a fixed point to find the tangent line and compute the rest. Okay, so that was the progression of the approximation. Let's just stick with Calc 1. How do we do this in Calc 1? I know this is my function. Let's find the derivative of that. So the first step, you decide about the function. Then you find the derivative of that, which is 1/2 of x to the power negative 1/2. This is step 2. Then step 3 is to decide where this function is easy to compute. And I know at x equal to 4, f of 4 is going to be square root of 4 equal to 2. Okay. So you write the tangent line at x equal to 4. What's the tangent line at x equal to 4? Let's first find the m. I have to plug it into f prime, which is 1/2 of 4 to the power negative 1/2. That gives me 1/4. Then what else do I need? I need to find the f value at which I found. Here's the f value. F of 4 is equal to 2. Then I write y is equal to 1/4 times x minus, what's the x value? 4, plus the y value, which is 2. I think when we wrote the equation of tangent line, 2 came first, and then the rest followed. And so let's annotate this a little bit more. This part, finding the tangent line. So I found f prime using this part, and f of 4 using that part. M goes here. 4 is the nice point. 2 is the y value of the nice point. And this becomes my tangent line. Now, step 5. Again, let's write down the tangent line. L sub 4. The nice point was 4. Nice input point was 4. Is equal to of x is equal to 2 plus 1/4 of x minus 4, right? Now plug in the point that you're approximating for, the input that you're approximating for. What is that? That's the input. So you plug in f sub 4 of 3.98, and you get 2 plus 1/4 of 3.98 minus 4. And then you compute that value, and that's going to be your approximation. So I had to go back. The space in here was smaller. I'm sorry that I went from this step to this step. And so at this point, all you need to do is, this is negative 0.02 times 1/4 plus 2. And this is going to give you 2 minus 0.02 divided by 4 is going to be 0.0. 2 and 2 simplify. 1 divided by 2 is 0.5. And then this entire thing is going to be 1.995. And so this is the approximation that we have. So we approximate this with 1.995. So it's much better approximation that you did in grade school, which was 2. You have a better approximation in here. And again, the reason we were allowed to approximate it 4 was that 4 is your A here. This one is your A. B is very close. 3.98 is very close to 8 as far as I'm concerned. And that's why we use the linear approximation to calculate the value basically. And now look at the picture. So in here we figured out this value. The actual approximation, this is really what your calculator does with Calc2 information, is 1.9949. Look how close this time I got to the actual value. And then this approximation is very nice. Now let's look at the picture. This is point A is 4, f of A is 2, and this is the tangent line, right? And so look at this. As as I'm getting closer and closer to 4, this tangent line value, y value on the tangent line and y values on the blue line get closer and closer to each other. It's actually that's what we realized. When you're very close to 4, it's very difficult. Right there, for example, it's very difficult to see any difference, and we saw that easily because the error that we found in the previous page was 0.00 0.0001 or 002, and so it's becoming very, very small and difficult to see. But if you go further, like at this point, if you pass 8, if you plug in points bigger than 8 in the tangent line, you start seeing errors a little better. Now, compared to a little bit of the values, so obviously we're approximating using 4, right? And for 3, what the actual value is of square root is 1.4. So at 3, the actual value is this. The linearization gives you this value. So if you subtract the 2 and divide by the actual value, the absolute value of that is just 0.1%. And then if you plug in 3.9, the actual value is here. What you get from tangent line is that. Subtract the 2, divide by the actual value. This is the percentage error that you get. Again, this is the point we're approximating at. At 4.1, you get this value. So again, if I write this, you subtract that, take the absolute value of this, divided by the absolute value of the actual value, and you get this percentage, and so on and so forth. This is called the percentage error that we're gonna discuss soon.